Thank you and good afternoon, everyone. We're going to talk about 3D printable geopolymers and foams. It's kind of an offshoot of a lot of other work that we've been doing. Got bored with printing regular cement-based materials, want to do something different. Students want to change, I want to change. So we're looking at something slightly different here in terms of 3D printing. And this work was done by my former student Suraj Nair, who is now with US Gypsum, and Hussam Al Ghamdi, who is with King Saud University in Saudi Arabia. So again, you might have seen these pictures enough number of times. I'm not going to get there. Generally, 3D printing involves printing mortars, even though with lots of new printers and new technologies, you can even print concretes, maybe to an aggregate size of quarter of an inch at the most. There has been work with cement-free binders, geopolymers, alkali-activated materials as a potential option. What we did in this work was to evaluate alkali-activated binders or geopolymers to look at what are the linkages between material design and processing parameters. A lot of our work is in the zone where, yes, materials are important, but materials are always linked to the processing parameters. If you don't take the processing parameters into account, for example, if you have two printers in your lab, you will notice that what you can print well with one printer is not something that you can print with another printer with a slightly different nozzle characteristics, a slightly different pushing mechanism, whatever that is. So processing also becomes very important. And of course, what we also want to look at insulation and how do we do geopolymeric foams for insulating and get as close to XPS polystyrene kind of materials as insulating materials. So for example, if you're building a wall, can you do co-printing of the insulating foam also along with the structural component of the wall? Right. So again, the idea that just to get the idea that we have the system characteristics, the printer characteristics, as well as the material characteristics that influence the output. There was a talk in the morning where we talked about buildability to look at how well you can build up structures. This one is a little different in that we are looking at mostly extrudability and printability, assuming that we are mostly focusing on the material design with a particular print configuration. Right, so printability, you want to have extrusion through a tapered nozzle. You should have the stability of the printed shape. So we looked at several mixes with lots of fly ash, some slag and some OPC to get some stability early on. We used aluminum powder in one of those mixes, not to foam. Typically use aluminum powder to foam, but we did not use it to foam. What we did was to control the setting time. A very small amount of aluminum powder will do wonders with the setting time, especially when you have lots of other materials that really doesn't aid in very early stiffening. Can you see liquid powder ratios? And so we used some limestone powder. Also, again, limestone, in all our work, we have come to love the use of limestone powder, even to 15, 20, 30%, because limestone powder with controlled particle sizes gives such a range of flexibility to use a lot of other materials. Not just that limestone does or does not do. We can have that debate in a completely different committee, but from a printability point of view, limestone does add a lot of flexibility to what you want to print. Right, so the classical rotational rheology that we all have become fans of, but we figured out that it's all nice to talk about yield stress and plastic viscosities in a rotational rheometer that you test to translate it into actual mix and see how that translates. You can get some, once you do enough number of tests, you can get some fits, but does that really relate to actual material performance? Big question. So we have used quite a bit of extrusional rheology, which I'll show you what that is. But just for sake of completion, yield stress and plastic viscosities that you want. And then if I want to quickly characterize based on what we did, stability with respect to yield stress, you will see this is basically yield stress slump is an expression of slump. This is basically what your slump looks like. This is a system with water. This is a system with sodium hydroxide, higher viscosity. You suddenly see the difference. So when you use alkalis, you can get much better shape retention and viscosity control. Right, so extrusional rheology, we'll talk about that in a minute. But if you look at time dependence of yield stress, you can have, as a function of time, you can measure yield stress as a function of time from the mix reacting with water or whatever solution it is. And we said, okay, here is a range that we can simply say, again, very, very arbitrarily, based on the extrusion setup that we had, based on the the rheology measurement that we have, we could simply say that this is a nice range in which we can say we have that a mix as a printable mix. But we also did remixing. So you see here at 0 minutes, so immediately after mixing, you could extrude. After 30 minutes, you could extrude. 45 minutes, you could not. But what happens if you remix after 60 minutes? Do the same thing, remixing. So again, if simulating the shear that you can have when you have the mix that's placed in your mixer itself. So what happens with extrudability? Now, with layering, what happens with open time, what happens with layer interface, a totally different question, which we will not get into now. I talked about extrusional rheology. So the idea here is, let me do this figure. The idea here is as a characterization technique, as not just a rotational rheology or shear rheology that everybody uses all the time. We simply used an extrusional rheology where you start to push this through a barrel, through a die of different changing cross sections. The idea that your material will start to undergo changes under pressure, under extrusion. And you can quantify that using a plasticity approach, a Benbow-Bridgewater model, from which you can get a yield stress and a wall shear stress that is related to the parameters after the mix is subjected to a certain process. What that gets you is actually the yield stress that you need to push through the material. Now, not all 3D printing apparatus uses a ram extrusion like that. You use a lot of screw extrusion as well. But in terms of material characterization, we have found this to be a much more simulative, much more better method than simply doing yield stress and plastic viscosity in a shear rheometer, whether you use parallel plate or a vane or whatever you want. So this is more of a material characterization tool that you can look at. And then for some reason, I did the figure that I want to get there before. So here is the extensional rheology, basically a tack test to look at how much adhesion is there. So energy required to separate the paste under normal tensile force, and this scales very well with alkalinity of the activator. And you can see that, and we have done some work where this factor actually is an indicator of interlayer bonding. So again, something that you can look at as a characteristic of interlayer bonding. Extrusion rheology. So basically, it's a force displacement relationship. You have an initial part where your extrusion pressure increases very quickly because ram is the piston is squeezing on the sample, a steady state where plastic flow is happening, and then once flow has happened, the mixture has changed its properties enough that it is now exerting resistance to flow. You will see an increasing in the stress that's required to extrude. So you can characterize these three zones, use models to come up with what the actual material properties are, which you can relate back to what either the time dependent or pressure dependent properties are. So here are some relationships with your yield stress from rotational rheology. You can have some kind of relationships, but we find that extrusion characterizes the material better, especially with different types of binders that you need, because otherwise you will just look at printability and extrudability by doing it, right? And then, like I said, the process, what system you use for processing also is influential, right? Compressive flexural strengths, I don't want to spend too much time on it, but you can say that 30 megapascal for 5 megapascal in flexure, fair enough. But I want to talk about something that's even more interesting for 3D printing, which is foaming. So what we did was to use we want to make it as simple as possible, not to use 15 different chemical components, not to use all those different foaming methods, just use a simple surfactant. Easily available, cheap, and see if we can get bubble stability under printing. Remember, when you have to go through this process of shearing within the printer and extrusion and layering, bubbles have to stay stable, right? So you really need to ensure bubble stability. We have parallels. We do air entrainers in concrete, and after all, you're pumping, the air stays stable, right? So it's not that it's unknown, but the difference is in a regular air entrainment, you're looking at 20 micron size air voids. Now here you look at millimeter size air voids. The larger the voids get, the larger the challenges with maintaining surface tension and bubble stability. So we looked at several different ways of doing it to control skeletal density, cohesiveness. We came up with one mix that we can use, and then a little bit of surfactant, 1 to 3% by mass. And we'd use a modifying mixing procedure. What we want to develop is a jammed foam. The idea is that you have to have each of those foam particles or the spheres reinforcing themselves. That's the idea of a jammed foam. So you don't want to have a foam at one place and nothing around it and the mix piles on it and breaks it. You don't want that. To have foam stability, you want lots of foams next to it, very similar to your critical distance and air void spacing when you do air entrainers. So same idea. So we used that idea and said, okay, how can we do that? Foam expansion retention. So we look at different surfactants, and you can see here with 3% surfactants, you'll see about 100% increase in porosity, which means the mix is expanding so much. Again, some shear yield tests that we did. But let me show you what happens. So we all talk about cement paste being yield stress fluids. We love it because yield stress fluids are easy to measure. If you can get some quantified values from yield stress fluids. Foams, once it gets to a jamming transition, when the bubbles are close to each other, they're jamming each other, which is about a 0.64 ratio, which you can simply prove if you look at a cubic lattice structure to fill out what should be your volume fraction. You will get something like 0.72 to be completely filled. You will get 0.58 if it's a simple cube, not very filled, 0.64 somewhere in between. It's a jamming transition. So below the yield stress, the foams behave as viscoelastic solids, and above the yield stress as non-Newtonian fluid. So it's very, very important to control that value. So what your rheological response, whatever rheological test, what you're getting is a competition between the skeleton yield stress and the stress which tends to deform the bubbles, and the capillary stress that is acting on the bubble that resists that deformation. So you have now two competing processes, and that can easily be explained using a plastic capillary number, a function of yield stress, surface tension, and the bubble radius. So you can look at bubble radius and surface tension being influential parameters if you want to look at, and you can see here what the yield stress is for 3 different surfactant ratios, and suddenly this is the yield stress for a mix without any surfactants or solid mix. You suddenly see dramatic reduction in yield stresses as you increase your surfactant volume. Now, with capillary numbers, we can see that, I know I'm doing the same equation again, let me skip that. But what you basically get is capillary number as a function of time helps us to understand the rheology better. And then capillary number and yield stress is also related. But again, pore size is important. So we have to do mercury intrusion porosimetry to find out what the actual pore sizes are. When the capillary number is less than 10, we'll find out that surface tension is dominant. Parametrically, you can easily figure this out. Yield stress is invariant of volume fraction at less than 0.5, which is 1% surfactant. But if you get to about 3% surfactant, which is greater than 0.64, jamming transition, your capillary number is more than 10, your bubbles behave as softer inclusions now. Your bubbles don't break, your bubbles just deform. Right? As you extrude through, bubbles deform, and once it's laid, it gets back. And if you want to look at buildability, here is viscosity recovery. That was the initial viscosity. You sheared it enough through the mixer to show what it's going through the mixer. You do it later, you're recovering most of your viscosity after, which means I'm not breaking down the mix enough for it to be not buildable. So something that is very interesting to look at. And here is a microstructure of 3 different foams. You can see some very nice jammed foam structure with a very rigid skeleton in between that doesn't. I'll show you one more thing. Give me 30 more seconds to do this. And what we did was, can we now use this in between a solid wall and print this as a foam, right? So basically, for different porosities, my thermal conductivity values for all those mixes were like this, but they were not small enough. It's only 0.15. If you use a polystyrene or expanded polystyrene that you use as an insulation in your wall in your house, that has a thermal conductivity of about 0.05. How do I get this to 0.05? Fair enough, if I simply use an effective model, I will get to about 0.05 if I have 60% air void fraction. Fill this. So this is a foamed material printed as a voided material. So print this. Now we can really print it well. So now you can actually start to get much higher thermal conductivity. You can start to co-print it also. So in summary, we have used alkaline activation as a way to decrease the shear yield stress, increase the cohesiveness, similar to use of superplasticides. I mean, very nice parallels between what you get when you use a high range water reducer for your conventional paste. We looked at a printability window. Extrusion rheology experiments coupled with a model gets you the extrusion yield stress, which actually explains what happens in the system much better. Of course, foam systems, which I showed you. Once you get to jamming transition, you can print them well. Not just print them well, you can print even lattices with them, which will give you extremely high thermal conductivity. Thank you very much.